Putala, good morning. Sorry, good afternoon.
Good afternoon, sir.
No, good afternoon to you. Had they nine, yeah. Had you joined right? Only 7. Also, we have one B.Ed student, Chandan. You are from manufacturing or mechatronics?
Manufacturing, sir.
Manufacturing. Okay, very good.
Manufacturing, sir.
Okay, very good.
Okay.
Especially when it comes to B.Ed also, you should understand the subjects to the very best levels so that you can contribute to the even to the education field. Yeah, that is very
Okay, sir.
important. Yeah.
Thank you,
Very
sir.
good that. Yeah, you like people are here really. Today, this isentropic expansions, we have learned about this last week, but it is really tough to share the things over the internet to the best levels because there are a lot of issues when it comes to the interactions. That's why. Anyway, we will try our best together to understand these things. So, I believe you can see this question. Steam enters a turbine operating at steady state with mass flow rate this. At the inlet, the pressure is 60. At the pressure is 0.1 bar, calculate the work done by the turbine and the surrounding in kilowatt. In kilowatt, if the expansion is isentropic. Yeah. So H1 minus H3 is W. For isentropic expansion, this is a TS diagram. This is TS diagram. Anyway, constant entropy you can see here S1 equals S2 equals S3. For non-isentropic, you can see 2 is 2 dash, 3 is 3 dash, and generally the entropy is increasing towards exit of the turbine. So this is how the entropy of the working fluid. You know, the working fluid means the steam goes in, turns the turbine because steam expands and finally leaving the turbine. So steam is the working fluid here. I believe you understand this very well. Even yeah, we managed to get H3 values. Yeah. Any question, any issues you faced when you calculate this H1 and H3? Yeah, we have to do some calculations. You have to calculate the X value here. I think it is okay. X value. If you need to calculate X value, let's say to go to the calculator. පුතා මෙතන නේද අපි එදා මේ ස්ටොප් කරුවේ? මතක ඇතිනේ? Yeah.
Yes, sir.
That is the calculator. So your X value is 6.541 minus 0.649. See, this divided by I cannot find the brackets in this calculator. Yeah, I cannot find the brackets. 8.149 minus 6 point, sorry, 0.649. This is something like 0, 11 minus 6, 5, 7.5. Always x is less than 1. 0.7856. Let me take this x as 0. Yeah. Okay, 7856. Okay, copy this. Copy. Then I can take x3. X3 is, yeah. Anyway, this times, yeah, x3 is, h3 is 2584 minus 192. Okay, 192. I can see a K here, but this is kilojoule per kilogram per Kelvin. Bracket. H is here. This, okay, is equal to 192 plus this is the x value times 2584 minus 192. 584 minus 192. This one equal to what? This is times here. 2584 minus 192. I will try to copy this to the calculator. Is it possible? Yeah. Sorry. A little issue is here. What I will do is, first I will take 2584 minus 192 here equal to this times 0.7856 equals this plus 192. 2071.11552. Yes, kilojoule per kilogram per Kelvin. So you can see H1 3177. Sorry, I made a mistake. This is not Kelvin. This is H. Okay, this is H, kilojoule per kilogram. Yeah. So H1 is 3177 kilojoule per kilogram. H3 of course should be lesser, 2071. Still quite high. H1 and H3, 2071. Is this okay? H3, that is at 0.1 bar. 0.1 bar. Yes, of course it is 2584. Is the HG. HF is 192. So in between, yeah, this is okay, 2071. Actually, you have to check how realistic. Whenever we get the figures, we should understand, or we should look, we should check how realistic the values are. That's why. So that is a separate knowledge to see how realistic the values are. So you have the H value. I calculated the H value here. 2071. Put it here. 2071. Because I have no idea how you can see this in your screen. Yeah, yeah, 2071. So you should have the units here and H1 value. At 1. Yes. Just 3177. Your H1 value. Okay. Kilojoule per kilogram. So then you can have your H1 minus H2 here. That is small w is H1 minus H2. Here you can see the work done for the turbines. Later I will share with you how this H1 minus H3. H1 minus H3 is the work done. W turbine isentropic. H1 minus H3. That is equal to 3177 minus 2071. Okay, 2071. That is equal to 3177 minus 2071 is 1106. 1106 kilojoule per kilogram. Quite interesting. Okay, 1106 kilogram. Ah, that is too big. Per kilogram. So then you know from here this one. So you have is the question. So H1 minus H3 you have here 1106 kilojoule per kilogram. This is for isentropic expansion. 1106 kilojoule per kilogram. Okay. So you have the mass flow rate kilograms per second is 4600 minus 3 divided by 3600. 46 by 36. 46 by 36 kilogram per second. This is 1.28. 1.28 equals 1.28 kilogram per second. Okay. So your m dot, the mass flow rate is here. Okay, your mass flow rate is here. Interesting. So mass flow rate is this one. Very nice. This one. Kilogram per second. So kilojoule per kilogram, this one. So W turbine isentropic per kg, this. So this is small w. So you can see W turbine, not for per kg. This is for total mass flow rate times H1 minus H3. So this is equal to, you have the values. One 1106
Sir,
kilojoule
excuse
per
me, sir.
second. Ah, yeah. Okay, Buddha. Yes, thank you.
Sir,
Yeah, now okay.
excuse me, sir. We can see only the.
Yeah, now okay, Buddha? Now okay? Yeah.
It's okay, sir.
Yeah. So 1.28 kilogram per second times 1126 kilojoule per kilogram. This one. So you can see kilogram and kilogram cancel out. Finally, kilojoule per second remains. So 1.28 times 1106. 1.28 times 1106. Okay, 1106. This is 1415. Kilojoules per second. Kilojoules per second means kilowatt. 1415. So this is what the value here. So it is quite easy. It is not about the easiness, but it's about how important this evaluation. Okay. So but here the important, that is what we need. Not about the easiness. If you understand well, should be good. Yeah. So W turbine is 1415.68. W turbine.
Can you share the screen?
Okay, Buddha. W turbine isentropic is this.
We can't see.
Yes, yes, yes. Thank you. Yeah. W turbine isentropic is this. Isentropic is this. Now let's say, yeah, I have to continue this. So this is the point here. You have the isentropic value and your x value is 0. Where is x value? 0.78 for your x value. Well, 0.786. So your x value, your x equals 0.786. That's a point. Yeah. So during this expansion, the superheated steam, high pressure, high temperature superheated steam, so release energy. When release energy, pressure goes down because of expansion, and also no much of energy, so molecules coming together and then partially becomes wet or some liquid formation is there. That's why you have a dryness fraction. So if you take this one, copy this. here it's the same. So if you think of here at 1, if you think of x, x is not applicable because this is superheated. You cannot say 1 or anything. This is superheated. X is not applicable. Okay? And slowly, what happens is the releasing of energy from the steam. So finally, X becomes 0.7856. X becomes 0.7856. So that is the X value. So we calculated this. This is for isentropic. Okay, for isentropic. Isen X is this. Interesting. If non-isen, that is a point, non-isentropic. How about X? X is definitely greater than X at isen. So this is the point. Okay, X is definitely greater than X isen means 0.7856. When it is non-isentropic. Okay. At 3. Okay. Isen X is 0.7856. Pressure is 0 at pressure 0.001 bar. Pressure equals, it's a 0.01 bar. At this pressure. Sorry, 0.1 bar, not 0.01. 0.1 bar. So you have noticed this. So for non-isentropic, X is more than this. Again at 0.01 bar. So I will put this like this. At 0.01 bar. Yeah, interesting. Okay, so this is the observation. Sometimes X can even, you have to say X is greater than this, and even can be, superheated. Superheated means X is something, not to say X something, even can be superheated. Heated. Heated means X is not applicable. Okay. X. Let's say the best example is this. Like this. Okay, this is okay. But you imagine, now I will copy this again. I will copy this. How come not applicable? It is because of this way. you have this. So not applicable means it is like this. Here close it to 3. See, like this means it cannot release the entire energy. So partly still the pressure is low but entropy is high. So you have the exit point 3 is like this. So it is something like 2 dash and 3 dash. 2 dash is here. 3 dash can be here. It's superheated. Funny but possible if the expansion is so bad. Means it's lot of losing of the useful energy. Not to becoming turning into useful work. Yeah. So can be like this even. Okay. This is TS diagram. Or sometimes can be like this. Okay, can be like this. So 2 dash and 3 dash is like this. Sometimes can be like this. So then the situation is here x is 0.7 what 0.7856 0.7856 okay 0.7856 here okay sometimes can be more than that. So let's say x is 0.9. So then it is surely non-isentropic. Yeah. So you have different 3. So it is something like 3 dash. X is 0.9. Or even at 3 dash. Am I sharing the right thing? Yeah. Okay. Sometimes 6. So superheated, not applicable. So here, what happens is pressure drops to certain level, but still you have certain superheat. So that is how the situation. Then what will be the enthalpy levels? What will be the enthalpy levels? Okay, very interesting. So here, enthalpy levels. So same pressure, you can see 3 dash high enthalpy. So H1 minus H3 dash is less when 3 dash enthalpy is high. Okay, so isentropic, it has the lowest enthalpy. So if I look into a try to understand. Try to understand. I take this part. Okay. So here, lowest enthalpy here. Okay. So here you have the lowest H3. The lowest H3 is here. Lowest H3. Lowest H3. So that is isentropic. Okay. Here you have the highest H3. Highest. Oh. High. Highest H3. So this is also a little high. High H3 here as well. Okay, high H3 here as well. So then you can see W is H1 minus H3. Okay, yeah, you cannot say it well. W is H1 minus H3. So when you have lowest H3 is highest W. Okay, this is the highest W. So highest W. Highest W, lowest H3. Interesting. Let's see. Here, highest H3 highest H3, lowest W. Okay, simple W, and also the big W also lowest. So you have to have this understanding very well. Okay, without writing equations. So when steam expands, isentropically means your entropy remains the same, means your loss or unavailability of thermal energy for useful work remains the same. Means the balance is of course taken, delivered as work done. So that is the maximum. So the other two you can see entropy is increasing. More increasing means more unavailability of thermal energy for useful work means less useful work means less W. So you can see here. You can see it here. That's the situation. Okay, that's the situation. I hope you can understand this. So if you go to the question, okay, this one, yeah, it's almost the same, you can see, but see, the steam enter turbine, it's the same thing. Okay, it's the same thing. It's the same thing. Enter the turbine and deliver some work. Give me a second. It's the same. Okay, it's the same. So 4600 kilogram per hour. It's the same like the previous question. Yeah. Develops a power output of 1000 kilowatt. Let's say I'm going to modify this. Delivers a power output of 1000 kilowatt. Let's say this one I'm going to modify. Another question. Oh yes, here. So I take this. I have the question. Now let's see. I take the turbine delivers power output 1000 kilowatt. I take it out with the purpose. Okay, because still we are looking into the W as H1 minus H3. Okay, W as H1 minus H3. So this is what we are focusing. Okay, W turbine as H1 minus H3. H3 dash. Actually, it is H3 dash. Dash is what the real. Yeah, real. So you have some expansions now. You can see because at the exit pressure 0.1, now you have dryness fraction 0.9. Okay, and I take this all out. Save it. Okay, I take this all out. So the actual question still I leave it here. And modify later, we will come to the original one. Step by step. See? Same. Exit point 1, now you have dryness fraction of 0.9. Yeah. See? Exit velocity also we take out. Now, calculate the work done by the turbine. Okay. Rate of heat transfer also take out, because we are learning step by step. So now you cannot see expansion is isentropic, because when isentropic, you know your x value is 0.7 something. You got it here. X isentropic. See, 0.1 bar. So this is the question. So you can see. We'll make it a little bit big. Okay. This is our finding. At 0.1 bar, isentropic is this. Yeah, that's why. So you can see that. So non-isentropic means we have x value 0.9. Yeah. So you have this. How to say? Copy. Paste. So now see, x is 0.9. So you have a little high H3. Okay. So you don't have the highest W, but you have a certain W value for x equals 0.9. Still W is H1 minus H3 dash now. Okay. H1 minus H3 dash. H3 dash. W is H1 minus H3 dash. Yeah. Now you have to look for H3 dash. Okay. So this is H3 dash. H3 dash. Yes. H3 dash is little high. Okay, H3 dash is a little high. Yeah, so x is 0.9. So you have to look into this. At x equals 0.9, your pressure and all remains the same. So this is your situation. Okay, this is your situation. Interesting. You can go here. See, your x is 0.9. It is 3. Okay, S3 equals S1, no such thing now. Where? It is 3. At 3, S3 is a question now. Yeah. But still, let's say at S3 is equal to this. So this is H3, eh? Yeah. X, no. S3, you have X1, X3 dash 0.9. See, now this is the one. But of course your HF, HFG all remains the same. So you substitute 0.9 here. Now you can get H3 dash. Understand? Yes, H3 dash. Because here, H3, is 3. You can write, you know, your Hg value. X is 0.9. It's given. And your Hg value, you can write Hg is 2584. Kilojoule per kilogram. Then your HF value, you have 192. Okay, kilojoule per kilogram. Okay, with steam, you have the X value given. With steam, 0.9. With steam. So X is 0.9. So you can find H3 is HF plus X times Hg minus HF. Now I'm calculating, you are watching at this. So you feel comfortable, but you have to have a good focus for that. Eh? That is very important. Yeah. This is one. Units you have kilojoules per kilogram. Okay, so your H3 is calculated 0.9 times this. Let me take this out. 0.9 times, yeah, I'll leave it. 0.9 times this. Yeah, okay. Now you can calculate this. 0.9 times 2584 minus 192. So let's say we will go to the calculator. 2584 minus 1. 2392 times 0.9, that is x, equals this 2152 plus 1 2344.8. I'm very sure this H3 should be more than isentropic H3. Okay, this has to be. Okay, 2344.8. This is where H3 calculation. H3 calculation is here. Okay. Yes. Okay. Yeah. 2344.8. So what is this? Is H3 dash. This is H3 dash.
So we can't see, sir.
Okay. Okay. Thank you. This is H3 dash. Yeah. So W H3 dash is this 2344.8. H3 dash. Yes, you can see. But in previous case, what is H3 value? 0.78, sorry, 2071 is the H3 for previous case. Okay. If I put it here, this is the previous case. Isentropic H3 is 2071. Now, not isentropic. Okay. Now, H1 minus H3 is 2344. See here, 2344. Now, 3177 minus 2344 is something different. Okay. 3177 minus 2344. 3177 minus 833. See, this is 833 kilojoule per kilogram. W turbine. Okay. Kilojoule per kilogram is 833. Earlier it is W isentropic. W turbine isentropic earlier. It is 1106. Okay, it is 1106. So you can see 1106 when isentropic expansion, and 833 when it is seems to be the kind of actual case. Okay, so that's what you should see. The isentropic expansion, it is more work delivered. Non-isentropic, less work delivered. So now you can go for the calculations. Same like the previous one. Yes. Now the situation is same W turbine, not isentropic. The isentropic we can leave it. W turbine when x equals 0.9, W turbine at x equals 0.9. Isentropic at x equals 0.7 something. Yeah? At x equals, let's see, 0.7856 at x equals. X equals this 0.7856. So this at x equals 1, H1 minus H3 is, yeah, mass flow rate times this is W2 non-isentropic, x equals 0.13, sorry, 0.9. UH1 minus H3 is, what's the value? 833. 833. Okay. So now W turbine at x equals 0.9 mass flow rate times H1 minus H3. So here should be 833. 833. So 1.28 times 833. It's a different value. 1.28 times 833. 0.28 times 833. After this, you are going to learn a very good piece of knowledge afterward. Eh? This is 1066.24. See, 1145 changed to 1066.24. See, this is W isentropic. Now, this is the W value. So let me make this, change that. I will take the question out here. I will move this up. Yes. Further, maybe I will make the font size a bit small. Yeah, good. 28. That's 32. Good. So W turbine is this isentropic. See, W turbine isentropic is this, but W turbine non-ison here is 1066.24. Okay, so that's why. So from the ideal, isentropic is considered ideal to something like actual is non-ison is considered actual. So efficiency, we can see isentropic efficiency. Just put isen for convenience is the W actual divided by W isen. Okay, isen. So this is the isentropic efficiency. So you can say this as 1066.24 divided by 1106. So it is not 1106, 1415.68. Okay, 0.68. Also, you can even consider small w, that is 833 divided by, how to say, 1106. Both are the same. Okay, 833 by 1106. Okay, 833 by 1106. Eight three three by 1106. Yeah, 0.7531. Okay. 0.753 2, let's say. This is 75.3%. 75.32%. It's quite interesting. Okay, quite interesting. That's how it is. See, if the expansion is isentropic, actually is isentropic, then the isentropic efficiency is 1 or 100%. But of course, actual is less than the work done when the expansion is isentropic, then you have a percentage. You know, this has something, a closer value, 75 to 80 is the isentropic expansion efficiency. Isentropic efficiency of engines, even compressors, turbines, it's around 80%. Early 80 is much lesser than that. So 75 to 80 consider very good. Yeah. So you can look into the literature. So you can see how best the isentropic efficiencies for the turbines, compressors, and even for engines. Yeah. There you can see isentropic efficiency. So even for refrigerant compressors, for the best compressors, you can consider 80% is reasonable. 90 may be too much. Yeah. 80% is okay. That's why I will share with you when you do the modeling. When you do the modeling of the compressors and all, this isentropic efficiency is important. Okay. I will show you one example. Yeah, I will show you one example. Let me go to the cool pack. Cool pack system. See, cooling cycle.
Sir, excuse me, sir.
Sorry, Bhuta, sorry.
It's okay, sir. It's okay. Sir, when we take the Hg value,
Yeah.
we consider the pressure 60 bar?
Yes, pressure is 0.11 bar at that case, Bhuta. Pressure is 0.1 bar. If I go to the question, see, this one,
pressure is
at the exit, the pressure is 0.1 bar. Pressure is very important measurement.
I mean, sir, 60 bar, that is the inlet pressure.
Inlet pressure is 60 bar. 1. At 1 pressure is 60 bar.
We should consider the exit pressure.
Exit pressure. And of course for inlet pressure as well, because here inlet pressure 60 bar, 400 degree, you have to take H1. See here, 60 bar, 400 degree is something fourth from the right. You can see 3177. That is H1 from last week. Question. Last week we worked on this.
Yes, sir.
Today is the analysis. Okay.
Okay, sir. Thank you. Thank you.
Thank you. So the analysis is continuing. That's right. So let me look into the cool pack. Where is cool pack? Cool pack. Yes, cool pack. Cool pack is this. Let's see. One stage cooling cycle. Okay. So I select this one. Problem. This is here maybe. Yeah. Okay. Let's see cycle specifications. Finally, this window appears, and See cycle specification, cyclic. I will share with you as well. See, compression, isentropic efficiency. Can you see the cursor here? For this auto calculation, isentropic is considered as 0.7. Okay, 0.7. Even you can change this. Then your cycle will be changed. Okay. So later we'll see how we can use this cool pack software. This is a free and a very good software. You can see the practical aspects of this. So we are learning the really practical things. So this isentropic efficiency is something very much important when you do the relative evaluations. For the initial cycles, you can go for isentropic of 1, but later you have to look into the real value possibilities, 0.7 or whatever, because of course we are not making compressors, but when we are using compressors for the systems, we have to look into this as well. But yeah, you can model this way, but when you purchase a compressor, you have to look into the compressor catalogs and the performance there. So that is the real ones, almost the lab scale ones. But for the modeling part, it is very important for you to look into the isentropic efficiency. So if you are smart enough, when you evaluate the data, you can see you can select the best compressors for that your customized applications. Later we will see this data. Now here I just want to show you that isentropic efficiency is one we are using in real cases. Yeah, that is very important. I believe you show that. So back to this presentation. So we know this. So this evaluation we have to continue one more step. Now we are going for the actual question. It is very interesting, really. Actual question. So step by step, we learn this. Yeah. So you are learning without your without any topics, but you are really learning. Yeah, that's right. So this question is for us to learn. This evaluation for us to learn. If you really follow this, you have taken a lot of knowledge. So let's look into the question now, the original one. Original one is here. Okay. Now here original one. The original one. Now reds are the additions. So I take this out. Okay, I take this out. Dryness fraction 0.9, I keep it. I take this out. The velocity 50 meters per second. I take this out. Still for this case, dryness fraction is 0.9. I consider this. Another velocity here in the 10 meters per second. I take that also out. You can see exit velocity is more. Inlet velocity is less. Exit is 50. Inlet is 10. You should know why, because when the steam leaving the exit or reaching the exit, it's a more volume because of the expansion. So you may have some understanding, so you have a bigger exit somehow. compared to inlet. So those are possibilities. Calculate the work done, and I put the work done by turbine. And rate of heat transfer also I keep it in kilowatt. This one also I keep it. Okay. Yeah. This is now quite close to the original, but still you have to go for one instead. Now we will see this case. So I take velocities also. Okay. Later I will explain why I took that. So this is addition. Turbine rate of heat transfer. Okay. Now I'm going to do this one. No. Wait. Okay, yeah, we will go with this. We will go with this. Not the question. Same mass flow rate. Turbine develops a power output of 1000. Yeah, now it says the power output develops the power output of 1000. Yeah. Yeah. It says it develops the power output of 1000. Yeah. At the inlet, this is this. Yeah. So develop the power means you no need to calculate the work done, because work done was given there. But what is the earlier work done? 1066. But now this says work done is 1000. Yeah. So this is the question. So this is the question. Sorry. This is the question. This is the question. Same rates. Now this is power output of 1000. At the inlet 60, same. Leaving pressure 0.1 bar. So inlet temperature 400, same. Dryness fraction 0.9. So original. Calculate the rate of heat transfer between the turbine and the sun. So that is what it's asking. Okay, that's what it is asking. Okay, now we have to have a different. So let's together explore this. Now, yes. So this is how it is in, out, and there is a work done. Out and work done. Now you have a work done mentioned here. W turbine is 1000 kilowatt. Okay, and your dryness fraction means X is 0.9. Here, so dash, you can see X is 0.9. X is 0.9. X is 0.9. At 3 dash. See, X is 0.9. Of course, you have idea about the inlet. 60 bar, 400. This is inlet. Yes. Same way when leaving, you have 0.1 bar. The temperature also given there, 0.1 bar. Okay, 0.1 bar. You have an X value, 0.9. So your temperature is there. Okay, you know these things. Quite interesting. Your H value here at the inlet. At the inlet. bar, 400 degrees C. How the H value? H1 is interesting because like this. Even at H at 3 dash X equals 0.9, you have calculated H3. You have calculated it somewhere. See, H3, 2344. Your H3 value. H3 dash is 2344. Okay, H3 dash is 2071. Sorry, 2344. 2344. Right? 2344. 2344. It's 3 days. Sorry. Yeah, 2344. So it's 3 days. Okay. Now you have a W turbine. Somehow you have W turbine. Okay, W turbine is 1000 it is given. So calculate the heat transfer between the turbine and the surroundings. So for this case, earlier cases, in the very first one, isentropic means no heat transfer between the turbine and surrounding. But now, there is a heat transfer between turbine and surrounding. There is a heat transfer between turbine and surrounding. Okay. This is the actual case because you know that turbines exterior is very hot. So it is really the other way from surrounding to turbine, not that way. From turbine to surrounding is the way because turbine is very hot. But anyway, as a standard, always heat transfer we consider towards the system. Okay, so let's see this one as Q. Q, heat transfer between surrounding and the turbine. Okay. Q. This is Q. Okay. We'll do this. Q. Now, heat, there is an input. Okay. W is the output. Okay. Heat is the input. W is the, so heat as an input. W also we consider anyway this an output. So this is anyway heat transfer from the surrounding, and you have real energy in with the flow. E1 is here, energy in E1, energy leaving E3 dash. Okay. So I will take this way. So I will take now energy here. Okay. E1. Okay. Of course, there should be energy flow with the working fluid. Energy flows. With the working fluid, energy is fully packed. Okay. And now, leaving here, little energy somehow leaving, that is E3 dash. So I will use 1 and 3 dash for the moment. Because we have used 2 somewhere else. That's why. Otherwise, your exit can be 2. 2 I put at the middle. Okay, E1, 3 dash. So W here, Q. So energy, you know, in first law of thermodynamics, energy has no end. To say energy cannot be created, no, destroyed. So energy is energy has something like conservation or the conservative property. Energy is, cannot be destroyed, cannot be created. So whatever the energy here, there is a balance because of the first law of thermodynamics, there is an energy balance. Okay? Because energy cannot be created, also cannot be destroyed. We call it conservation of energy principle or first law of enthalpy. Later we will see, don't worry. So before that, before learning the first law, we are going for energy balance. See here, as I say, for the turbine, E1 is coming. Okay, E1 is coming according to the arrows. Then you have Q. Q also relation here. I just follow the arrows. Leaving this, okay, leaving this is, as I say, W turbine is leaving. Another leaving is E3 dash. Okay, E3 dash is leaving. Entering minus leaving. Okay, entering minus leaving is what we need. Okay, this is what the increase means, the rise, because comes in, goes out, and there is a balance. There is a balance. Let's say delta E. What is this? Delta E of the, within the turbine, we will call this system energy. Where is this? Increase. Delta E system. Okay, delta E system. Delta E system. Delta E system. Oh. So delta E system. This is okay. Delta E system. Energy level drive. Okay. But okay, this is a rate per hour or per second or watt. So when you have a steady energy force, or steady flow energy, okay, so delta E system can be zero for steady flow energy. Flowing. That is a flowing. Okay. Steady flow energy. So I can take this flow out. Steady flow energy. There is a steady flow energy. For steady flow energy. Little smaller. For steady flow energy. Okay. Delta E system. Then you can see, you can simplify this energy balance.
Sir, excuse me, sir.
Yeah,
So can you explain again about Q, sir? Q, that Q mean
Q. Q
that
is
when the system is running, the
this
power.
is the Q.
energy is going to the outside,
Yeah,
or
okay. Calculate the rate of heat transfer between the turbine and the surrounding. So I just put this as Q. This is Q. This is Q. Okay, this is Q. This Q is here in this picture, in this time. So generally, there is a heat transfer between turbine and the surrounding. There is a heat transfer between turbine and the surrounding. Because turbine means here the gas or the working fluid expands and produces some work. So in this arrangement, okay, this turbine is not insulated. Okay, not insulated, and turbine considered quite hot because inlet is 400 degrees Celsius. Lot of energy coming, so there should be a heat loss. So we call it heat transfer between heat loss to the surrounding means heat transfer between turbine and the surrounding. So this Q, I consider this direction. Of course, Q can be a negative answer. Understand?
okay, sir.
Yeah, Q can be a negative answer. Okay, Q can be a negative answer. Okay, so delta A system is 0 for steady flow energy. So then, with this assumption, we can say, I have to go for a new slide. With this assumption, so let me make the question a bit smaller in font size. So know the question. Okay, for steady flow energy, delta is 0, so we can have this expression. So you have energy in with the working fluid inlet and energy leaving with the working fluid outlet, and there should be a work done, we call it W here turbine, and then there should be some heat leak from the system to the surrounding. Heat leak we consider arrow direction Q towards the system. Okay, towards the system. So if this is the case, then if steady flow energy condition, for steady flow energy condition, so delta E or the energy rise becomes 0. Okay, energy rise becomes 0. So this is the situation. Okay, delta system. Delta E is 0 for steady flow energy condition. Then E1 minus Q. Okay, E1, sorry, plus Q minus energy out from the system, that is W plus E3 dash. Is 0 means no rising, no reducing the system energy within the system. Whatever remains from the beginning, it remains. So anything comes in, goes out. So that is what we call the steady flow energy equation. Okay, steady flow energy equation. When this is 0, we call this steady flow energy equation. Okay, quite interesting. Steady flow energy equation. This is SF. Okay. I will take this here, separate, and starting here, if I divide this, let's say it is okay, E1. Okay, E1 is okay. We will do this way. So per unit mass flow, means 1 kg per second. I will write this per unit mass flow rate. I will write this. This way. This is E1. Okay. This is small q. This is small w. This is small E3 dash. Okay. Actually, we have discussed earlier steady flow energy equation. We have discussed earlier very briefly. Okay. Somewhere. So for this case, I will take E1 as H1 assumption, E3 as H3 dash assumption. Okay, E3 as H3 dash assumption. Okay, E1. Later, we will see the possibility of this. H3. Okay, so these are the assumptions. Assumptions. Later, we will justify. Justification is next week's session. So from here, you can take the work done. What is asking? The heat transfer between Q. You can say Q as from this equation. You can derive Q is equal to W plus H3 minus H1. H3 dash minus H1. H3 dash minus H1. It is 330. But you have to be patient to be 3 dash minus H1. Okay. So per unit mass. So what is W? H3 dash minus H1. one is W. W is 1000 divided by your mass flow rate. That's like per unit mass flow rate means you have to divide it by 1.28 kilogram per second divided by 1.2. Okay, plus H3 dash, see, 2344 kilojoule per kilogram minus H1 3177. You can see 3177. Okay, this is the answer. So you go to calculator, you can see.
So that
Sorry,
H1
huh?
H1 is there is again H1, no sir?
H1.
Did not.
H1, that is 60 bar 400 degrees Celsius.
No, I mean, sir, it is not remove that line, the upper line, not last one, the upper line.
Here,
You take it to right side, sir, then it should be removed.
W plus H3 dash minus H1. That is okay with that?
Yes, sir.
Yeah, I put H3 dash. Yeah, I can take the bracket out. That is okay. Yeah, we can take the bracket out. Done. Yeah. Okay. H3 dash. I think this should be okay with that. W is this per kg per second is this. So plus H3 minus H1. H3 dash 2344 minus H1 3177 is here. So let's say 1000 by 1.2. Correct me if I'm wrong to that. This plus 2344 minus 3177 minus 51.75. Okay, that's right. You can see this is minus because heat is not towards the turbine, that is from the turbine. This is kilojoule. Per kilogram per second. Okay, because this is the situation. Kilojoule per kilogram per second. Okay, so big Q is, okay, big Q is the small q times. Yeah. I saw the, I understand what you mentioned. Here it should be only Q. Okay, thank you. Okay, this is. So your big Q becomes small q times your mass flow rate. This one. per kilogram per second, you see. 1.28 gram per second. So this is a big cube. It is minus. Okay, this is minus. So you kilogram per second, and this kilogram per second cancel out, and you have 1.28 times minus 51.25, 51.75. So you will have a value that is minus 1.28 times 51.5 times 1.28. It is the value 66.24 minus 0.24 kilowatt. Kilojoules per second is I made a mistake of the units. This is kilojoule per kilogram. Huh? Yeah, I made a mistake. No second here. Kilojoule per kilogram. So kilojoule per kilogram. So kilojoule per kilogram. No second here. Huh? No second. So then this is kilojoule per second. Second remains. This is kilojoule per second. Second equals kilowatt. Okay. Minus.
So we can't say that.
Somehow and this. I make the fonts small. This. Okay. This is your answer. You can check. Right? You can check.
So screen is still calculator, sir.
Sorry, Bhutan?
It's still in calculator, that screen is our screen.
Okay, okay, okay. Thank you for responding. Right. So that's how it is. So here we are using the steady flow energy balance. Okay. Energy balance, and finally it is for steady flow energy balance. Right? That is steady flow energy balance. So steady flow energy conditions, we call this steady flow energy equation. So you can have in any terms, but this is the formulation. Right? So coming week, we are going to study the steady flow energy equation. In the first law of thermodynamics to the open system, we are going to learn coming week. The reason is here, in the coming week, in the question, we are going to consider everything. 10 meters per second, and also 50 meters per second, we are going to consider. Okay? Then that will be for the steady flow energy equations. When you know this, I think you have learned something sufficient at start. But we have to learn some more. But we are on track. We are on track with the blend of some practical applications with some principles. So if possible, if you have a computer, even for mobile, you can download Toolpack. Would be useful. Okay, Kutana, so this is end of today's session. And I believe we are doing all right, but if we can see face to face, this will be quite wonderful. This will be quite wonderful, but anyway, we will proceed whatever with the available options. And one day, hopefully, see you face to face to resolve whatever issues remain. Yeah? So thank you very much for responding. And also thank you very much for joining. Today, participants looks less, but we have done something good. Because slowly we are learning. Once we come to tomorrow's session, I think thermodynamics, I would say 50% done. Because you know a lot now about entropies, energies, and the enthalpies, internal energy, and so on. The isentropic efficiency, you know the basics. Yeah. So after next week, we will be on more practical applications like refrigeration and air conditioning. Power plants we are going to analyze. Then there's some theoretical cycles, Carnot cycles, Rankine cycles, and all the cycles we are going to analyze. So everything becomes easier. Compressors, nozzles, diffusers, lot of things. Even capillaries. We will see how to model this based on our first principle model. Yeah? So by the way, do you need today presentation? I can send 2 days combination this one. This is 17 today. 17. 10 plus 10 and 17 combined. Yes, I found it. BTech Met 19. Good. Today presentation. Today presentation. You will receive the presentation now. Items. Yeah, looks delivered. So, see you next week.
Thank you, sir.
Okay. Thank you very much for joining.
Thank you.
Bye.